this is the third lecture in our series on error correcting codes, and as before, what I would like to do is I will begin with a recap of what we did last time. In a nutshell, what we did last time was look at some examples codes and their parameters, and then towards the end of the last lecture we tried to say, well, supposing you have a code whose minimum distance is such and such, then how does that relate to the error correcting capability of the code, and we were in the middle of that proof. So, we will pick up from that point onwards. So, first what I will do is I will just go over the material relating to example codes and their parameters. We will go over that quickly, and then after that I will come back and talk about and continue where we left off in the proof. Okay. So, here if you go down to the pad here, you see that example codes and their parameters. I first introduced the repetition code. In the repetition code, all the symbols are the same. So, the parameters of the code are the following: the size is 2, the rate of the code is 1/7, and the minimum distance of the code is 7. The next code was the single parity check code, and here the condition on for membership in the code is that the sum of the symbols must actually be 0, and as a result you find that the size of the code is 2 to the 6, the rate is 6/7, and the minimum distance is 2, and these are two example code words whose distance is 2. Then the Hamming code is defined a little bit differently. I explained it in terms of these 3 circles, and I said the way it is defined is by introducing certain message symbols M0, M1, M2 and M3, and then filling in the corresponding parity, and that gives rise to these equations. And from these equations it is possible to actually determine the parameters of the code, which in this case turns out to be, so the size of the code is 16 because there are 4 message symbols, the rate is 4/7, the minimum distance you can show is 3, and I left it to you as an exercise. Later on we will actually see an alternative and perhaps simpler way of actually proving that the minimum distance of this code is actually 3, right. So, now next I am moving on to talking about the relationship that exists between the minimum distance of a code and the error correction capability of the code. So, for that we begin with a definition which says that a TC/TD code is a code in which any combination of less than or equal to T sub C errors can be detected and corrected, and any combination of T errors where T lies between T sub C and T sub D can be detected as an uncorrectable error. And in this pair we will always assume that T sub D is greater than or equal to T sub C. So, whenever we define this, it will automatically be implied that while this can be the same as this, the second parameter T sub D can be the same as the first, in general it is larger. Okay. And the theorem that we were in the midst of proving is that a binary block code C is a TC/TD code if and only if the minimum distance of the code is greater than or equal to T sub C plus T sub D plus 1. And now IFF here means if and only if, so which means we have to prove 2 things. One is we have to show that if this condition is satisfied, then the code is in fact capable of correcting T sub C errors and detecting T sub D errors. Okay. So, we went through the proof of the if part. I will go through that once more again and then pick up for the only if part. So, let us assume that in fact you are given that the minimum distance of the code satisfies the condition that D min is greater than or equal to T sub C plus T sub D plus 1. And now we are going to show that the code can correct T sub C errors and detect T sub D by exhibiting a particular decoding algorithm. So, the decoding algorithm runs as follows. So, by the way, one definition that we use here is that of a ball. Given any vector A and given a real number r, which we think of as the radius, the ball surrounding the vector is the set of all n tuples where the Hamming distance between A and Z is less than or equal to r. Okay, so that is what we define as a ball, and what we have shown in this figure here is that here is your received vector y, and our decoding algorithm proceeds as follows. We will first of all examine the ball centered at y whose radius is t sub c, and that is the green circle that you see on your screen. Now, given that ball, what we are going to do is we are going to look to see if there is a code word that is contained within the ball. Now, it could be that there is a code word, it could be that there is more than one code word, or it could be that there is no code word. All right. At the outset, these are the possibilities. We will narrow down the possibilities as we go along. Now, okay, so we will first examine the ball or the neighborhood of the vector y whose radius is t sub c. If there is a single code word in that ball, then we will actually declare that x was the transmitted code word and decode to x, and the decoding algorithm ends there. Now, on the other hand, if we look at this ball and we find that there is no vector contained in this ball, then we will say that an uncorrectable error has taken place. All right. So, this is very simple. There are two cases and we take different actions depending upon which of the two is actually true. Now, to show that it actually works, let us examine what could possibly go wrong. Now, there is this other possibility that maybe that is running through your mind. What if this ball contains more than one code word? But as we will see in the proof, that is not going to be possible. So, I will not discuss that up front as a special case, right. So, here now supposing you look at the ball at y of radius t sub c and you happen to find that there is a vector x in it, and then what you do is you declare that x was the transmitted code word. What could go wrong? The only thing that can go wrong is if x was not the transmitted code word, which means there was some other vector which was the transmitted code word. Let us put x tilde, x with a wiggle on top, it is pronounced x tilde. Let us say that x tilde was actually the transmitted code word. But one thing to keep in mind is that our promises with respect to this code are only insofar as correcting t sub c errors and detecting t sub d errors. If in fact it turns out that the number of errors is greater than t sub d, then we do not guarantee anything, we do not promise anything, we are not required to deliver anything. So, for that reason it is perfectly okay for the code to break down if the number of errors is more than t sub d. So, we will keep that in mind. So, here for that reason we can restrict our attention to the case when in fact the number of errors is less than or equal to t sub d, right. So, let us say that here is your actual transmitted code word x tilde, and if it turns out that that was not equal to x, then you have made an error. Okay. Now, my goal is to show that this cannot happen, because, and the simple reason for that is if you take a look, the distance between x and y, the distance between y and x is less than or equal to t sub c, simply because it belongs to the ball. On the other hand, the Hamming distance between y and x tilde is less than or equal to t sub d. The reason being that you are only confining your attention to these situations. All right. Now, if you put the two together, then what you actually have is that here, so after some discussion in which basically I expand on what I have just said, you have the situation over here where this thing here is your vector y received, you have x whose Hamming distance is less than or equal to t sub c, and you have x tilde whose Hamming distance is less than or equal to t sub d. But that would imply that there are two code words in the code whose Hamming distance is less than or equal to tc plus td, because this distance plus this distance is greater than or equal to the distance along the straight line path, right. So, let me just do one thing here. Yeah. So, the point is that the distance from here to here is less than or equal to the sum of these two distances, which must mean, as if you look at the argument on the right here written out in blue, the Hamming distance between x and x tilde is less than or equal to t sub c plus t sub d plus 1, strictly less, which is the minimum distance of the code. So, that is a contradiction, because after all no two code words in the code can be separated by less than the minimum distance. Okay. So, that proves that this situation, this picture that we showed up front is in fact not possible. It cannot be that the geometric picture looks like this. this picture is not a true picture, in other words. Okay. So, now that leads us to the other situation, which is, well, what if so let me repeat my argument. So, what if I have my received vector y and I draw a ball whose radius is, let us say, t sub c, and this time I am in the middle of my decoding algorithm and I find that there is no code word in this ball, and then the question is, what can go wrong? Now, so let me put that down. Suppose there is no code word to be found in the ball centered at y whose radius is t sub c. And then the question is, what can go wrong? The only thing that can go wrong is, because now what you are going to do is you are going to actually declare an uncorrectable error. Okay. V, by V we mean the decoder, will then declare an uncorrectable error. So, the only thing that can possibly go wrong is if in fact there was a correctable error. Okay, the only way we can go wrong is if there was a correctable error. But what does that mean? That means that the only way we could have gone wrong is if there was a vector whose distance, the only way in which we could have gone wrong is if there was a code word which was correctable. There was a code word and there was a number of errors which was correctable, which would imply that there was a code word whose Hamming distance was less than or equal to t sub c. But that is clearly not possible, right, because we started off, we looked at the ball, we found that there was no code word in there. So, there is no question of there being this other possibility. So, I am just going to, I have drawn this, but I am going to quickly rule this out just to emphasize that this situation is not possible, and clearly we cannot go wrong. So, the conclusion is that we cannot in this case go wrong. Clearly, the decoder will be correct, since the only way it could possibly go wrong is if there was a correctable error, i.e. a code word within Hamming distance Tc of y, but this is impossible by our initial assumption that the ball was empty. Okay. So, that concludes the proof of the if part, and it is possible that the first time you go through this you are still a little bit puzzled, but you just have to work this through out on your own. So, now I am going to proceed to the only if part. So, the proof of the only if part. So, here we actually show that the inequality that we had written down earlier was in fact necessary. Okay. So, we have to show that d min greater than or equal to t sub c plus t sub d plus 1 is in fact necessary. Suppose not. Suppose not, which implies that d min was is less than, strictly less than t sub c plus t sub d plus 1. Okay, let us say d min is equal to t sub c plus t sub d minus L, say. So, L could be 0 or larger than 0, right. So, let us assume that this was the case, and now but the fact that the minimum distance of the code is given by an expression like this implies the existence of a pair of code words separated by such a Hamming distance. Implies there exists. Okay, so, this symbol means there exists a pair of code words x1, x2 in the code C such that the Hamming distance between x1 and x2 is equal to t sub c plus t sub d minus L, right. And now, let us look at the following picture. You have on the one side you have x1, and then here you have x2. And now I am going to draw a line between these two, and let us say that now let us say I am going to put down a vector in the middle here, somewhere in the middle, and I am going to call that y, and by y I am using the symbol y as before to denote the received vector. Okay. Now, there is something to prove here. I mean, you okay, first of all, what do I mean by a vector lying on this line? What I really mean is that the distance from end to end on this line is t sub c plus t sub d minus L. So, let us choose a vector in such a way that the distance from here to here, from x1 to y, is in fact t sub d. Okay. So, this distance, let us say, is t sub d, and the remaining distance is, let us say, t sub c minus L. Now, there is something to prove here, because you have to show that given two vectors x1 and x2 whose Hamming distance separation is t sub c plus t sub d minus L, that in fact you can actually find a vector which is kind of in between them, where such that the sum of the distances from x1 to y and from y to x2 adds up to t sub c plus t sub d minus L. But that is fairly easy to see, because the meaning of Hamming distance or an alternative interpretation of the Hamming distance is simply the number of symbols that you need to change to go from x1 to x2. Okay. So, you need to change t sub c plus t sub d minus l symbols to go from x1 to x2. So, supposing I change t sub d of them and stop in the middle, then I will be at the vector y, and I need t sub c minus l more changes to get to x2. Okay. So, this diagram, in other words, this figure makes sense, and it is perfectly possible that x1 that you have a code in where x1 and x2 are the code words and where y is the received vector. And the problem here is that this situation presents the decoder with a dilemma that cannot be resolved, because what can the receiver do if it receives y? It's like the saying which says that I'm damned if I do and I'm damned if I don't, right? No matter what the receiver does in this situation, it's going to potentially be in error. The decoder being deterministic, given y, it has to say something. It has to either declare that there is an error and correct it, or it has to declare an uncorrectable error. Now, because the distance from x2 to y is t sub c minus l, which is less than or equal to t sub c, it is possible that y was the result of x2 being transmitted. So, with that in mind, the decoder, to take care of that case, should, given that y was the received vector, should have decoded to x2. But similarly, it is perfectly possible that x1 was the transmitted vector and there were t sub d errors. So, both possibilities exist, and they call for two different actions on the receiver in order for the receiver to be correct. So, it is impossible that no matter how you design the decoder, you are going to be in error in one of the two cases. You cannot be right in both cases, and that is why you cannot correct t sub c and detect t sub d errors if the minimum distance is insufficient. Okay, so, that concludes the proof. Okay, so, I will just make a brief note along the lines of what I have just said. So, we will say that the situation above presents the receiver with a dilemma that cannot be resolved for the case when y is the received okay. So, thus when d min is less than t sub c plus t sub d plus 1, a code cannot be a t sub c t sub d code, and that concludes this proof. Okay. And that was a lengthy proof, and perhaps you got lost in an argument along the way, but just keep the result in mind, namely that in order for it to be able to be a TC, it needs this inequality to be satisfied. And now let us go to our example codes. The first code being the repetition code. The repetition code, here the minimum distance of the code was 7. So, we saw this earlier. and therefore, we have the inequality T sub C plus T sub D plus 1, okay, that must be less than or equal to 7. So, the code is a TC-TD code for all pairs which satisfy this inequality. Now, the interesting thing is that since this inequality is all that is required, you can use the same code to provide different measures of error correcting capability. So, from this you can actually use the code on the one hand as a code in which T sub C is equal to 0 and T sub D is equal to 6. You could use it as a code for which T sub C is equal to 1, T sub D is equal to 5, right. And then at the other end of the spectrum, you can also use it as a code for which T sub C is equal to T sub D is equal to 3. Okay. So, you can use this code in these different ways. I guess the only one that is really missing in this list, so let me put that down as well. Is the case when T sub C is equal to 2 and T sub D is equal to 4. So, you can use this code in 4 different ways. Now, one thing that might puzzle you is how is it possible to use the same code to provide different measures of error correcting capability? And the answer is because remember that your decoding algorithm was centered around it involved using the value of T sub C, because remember we had that we would look in a ball. Let me see if I can find that for you. So, in our decoding algorithm what we actually did was we took the received vector, drew a ball of radius T sub C around it and looked for a code word, right. So, now if T sub C was larger or smaller, this ball will get bigger or smaller. So, the decoding algorithm changes with the parameter set that you actually choose, and this is what allows the code to provide different measures of error correcting capability, all right. So, this is for the case of the repetition code. Now, let us look at some of the other codes. Example B, the single parity check code. Here for this code, d min, if you will recall, was 2. So, since the minimum distance is small, that does not leave a whole lot of room for selecting your parameters, okay, according to so let us put down that equation again, that T sub C plus T sub D plus 1 must be less than or equal to d min. So, it does not leave very much room to play. In fact, the only thing that you really can do in this case is choose T sub C equal to 0, T sub D equal to 1. So, the code can only be used for detecting single errors, it cannot be used for error correction. Moving on to our third code, example C, which is the Hamming code. So, in the Hamming code, the minimum distance of this code was equal to 3. So, from this it is clear that the code can be used again with respect to our equation, which says that this code can be used in one of two ways actually. In one way you could use it as a T sub C equal to 0, T sub D equal to 2. So, you can detect 2 errors, but not correct any errors. The other alternative is to correct a single error, and this corresponds to the case when both T sub C and T sub D are both equal to 1, right. So, we have seen 3 examples of how the code's minimum distance and the associated error correction capabilities. Now, I would like to just say a few words about where we are going to go next. So, we have talked about binary codes in general, and now what I would like to do is focus on the subclass of binary codes, which are the so called linear codes. Now, linear codes essentially make use of linear algebra, but there is also a little bit of group theory, and since I assume that some of you may not have the a background in these two areas, what I will do over the course of the next 2 lectures or so is to actually try to fill in that background. So, we will make a slight detour, we will leave coding theory aside for the moment, and we will talk first about groups and subgroups, and then later on we will talk about rings, fields and vector spaces. Okay. So, that is going to require some patience on your part to sit through a couple of lectures where we talk about very elementary abstract algebra, and then we will come back to coding theory. Of course, the benefit of these lectures is if you have the background, you can just skip right ahead and catch up a couple of lectures later. Okay. So, I am going to go on to discuss some background on groups. So, I will entitle this mathematical preliminaries. So, we will talk firstly about groups. So, definition: a group G comma dot is a set G along with an operation which is dot, under which the following conditions are satisfied. First of all, if A, B belong to the group, then A dot B must belong to the group. This is called the operation of closure. If you have 3 elements A, B, C, then, and if you are interested in multiplying the 3 together, then the way in which you group them prior to multiplying does not make a difference. Then A times B C, B dot C. So, A dot B dot C is equal to A dot B dot C. So, you can multiply B and C together first and then bring in A, or you can multiply A and B and then bring in C, and it does not matter. So, this is called the associative property. The third property is there exists an element there exists an element E in G such that, so when I write S dot T dot, you should read that as such that A times E is equal to E times A is equal to A for all, and I will often use this symbol to denote all, for all A in G, then 4. So, this axiom is called the axiom of the identity element. The fourth axiom says that for every A in G, there exists an element which is called A inverse, such that A times A inverse is equal to A inverse times A is equal to E. Okay. And so, this is pronounced A inverse. Okay. And this is called the axiom of the inverse. Now, these four axioms collectively make up a group. Now, often the groups that we will deal with will be abelian groups. Furthermore, in the case of abelian groups, we also have that A B is equal to B A for all A B in G, and this is called the commutative property. Or the commutative axiom. And abelian groups, so that those are the 5 axioms that define a group. And just make a quick remark that note abelian groups are also called commutative groups. And it is not surprising, right. So, once again, just to quickly go through the axioms, there are 5 of them. You need closure, that is, if you now you can think of this operation as either multiplication or addition. Right now, it is just a binary operation. In our examples, it will often correspond to addition. What the first one is saying is that if you operate on 2 elements, you will get a third element in the group. and this is saying the order in which you multiply does not make a difference. There is an identity element which preserves elements upon multiplication. Every element has an inverse, and then for the case of abelian groups, and often we will be working with abelian groups, you also have the additional axiom that the elements commute under this operation, which means that the order in which you write them does not make a difference. All right. So, what are some examples? Okay. So, the first example is consider the set of all n tuples where the operation is plus, and by plus what we will mean here is modulo 2 addition component wise. Okay. So, for if let us say that n is equal to 3, in which case your group G, the group G will be comprised of 8 vectors, okay. So, your group G will be comprised of these 8 elements, and the way in which you actually add is component wise modulo 2. So, 0 1 1 plus 1 0 1 would be 0 plus 1 which is 1, 1 plus 0 which is 1, 1 plus 1 which is 0, because you are doing modulo 2 arithmetic, and you can check that the axioms are satisfied. For example, so can verify that in particular 0, which is the vector whose components are all 0, plays the role of the identity element. So, this is the identity element, and if you want, if you are thinking in terms of the inverse, let us say A is the element 1 0 1, and you might be wondering what is A inverse. Remember that A inverse is some element that has to be added back to A to give you 0. So, in this case, since you are doing modulo 2 arithmetic, A inverse is in fact A itself. So, it is equal to A. So, that is just for this particular case, right. And of course, addition is commutative here. So, this is an example of an abelian group. All right. Let us look at another example. Consider G dot to be Zn under plus, where this time plus denotes modulo n addition. So, what does modulo n addition mean? It means that so that means that a plus b is really the remainder after you divide a plus b by n, right? And z sub n is the set of integers modulo n, and strictly speaking it is a collection of equivalence classes, but we will choose representatives. So, we will pretend that this is just this particular set, the set of integers, all integers ranging from 0 to n minus 1. So, there are n elements in this set, and once again you can check that the axioms are satisfied. For example, the identity element, the identity is 0. If you take 2 inverse, for example, then or more generally if you take A inverse, if you look at and ask the question what is A inverse? A inverse is nothing but n minus A, and it is an abelian group. If you are uncomfortable with these sets and operations, you might want to go through the axioms and see for yourself and convince yourself that the axioms actually hold for this particular case. Now, there are some consequences of the axioms. That is, groups have certain properties that follow from the axioms, and therefore, which do not need to be stated separately along with the axioms. So, we will call these derived properties. So, the derived properties are these. First of all, the identity element is unique, because suppose not, and suppose that E1 and E2 were both identity elements. This would imply that E1 plus E2 is equal to E1, because after all E2 is the identity. But on the other hand, since E1 is the identity, that is also equal to E2. So, this implies that E1 equals E2, and therefore, that shows that the identity element is unique. The second property shows that even the inverses are unique. Every element has a unique inverse. How do we see that? So let us say, again suppose not, suppose both C and B are inverses of A. But this implies if you consider C times A times B, on the one hand you can say that this is C times AB, but because B is the inverse of A, that C times the identity which is C. On the other hand, you can group this and say that this is C times A times B, and because C is the identity, this is A times B, this is E times B, this is E times B, which is B. Okay. So, that proves that therefore, by comparing end results, we see that B is actually equal to C. All right. Then another property which you can I will leave it to you to verify as an exercise is 3. A B inverse is equal to B inverse A inverse. It is a very quick exercise. So, this is like matrices, just like this is also the case with matrices, but also holds here. Then 4, if you take the inverse of the inverse, then you will actually get the element back, also an exercise for you. Then the cancellation law holds. What does that mean? This means that i.e. if C times A is equal to C times B, that implies A is equal to B. You can sort of cancel C on both sides, and the proof is because C inverse times C A, if these two elements are equal, of course they will remain equal even if you multiply on the left by C inverse, but this implies that C inverse C times A implies is equal to C inverse C inverse C times B implies that E times A is equal to E times B implies that A is equal to B. So, the cancellation law also holds. If you take, and we are going to define, when we write A to the m, this will mean A times A times A times A m times, right. There is one more derived property in relation to this, but I see that we are running out of time. So, what I will do is, rather than go through that, I will continue that next time. I will just summarize what we have actually covered in this lecture. Let me see if I can zoom out so that we can see more of the lecture on the slides. So, we first completed the proof that a code is a T sub C, T sub D code if and only if the inequality T sub C plus T sub D plus 1 is less than or equal to the minimum distance of the code. We completed that proof. Then we went on to talking about mathematical preliminaries. We defined the axioms that go into making up a group. We looked at some examples, and then we stated some derived properties. Okay. So, with that I would like to close, and we will see you next time, where, as I mentioned before, for the next 2 classes we will be working on mathematical preliminaries. So, thank you.